So here we're going to take a look at fugacity and activity. Both of these items were invented by Gilbert Lewis between 1901 and 1907, and you can look up his original papers, and they're really very interesting to read. But we're not going to follow his derivation. We're going to follow a derivation that's really kind of a combination of Castellan and Nordstrom and Munoz, and they begin here. So let's say we have the Gibbs free energy of some substance, and we want to know what that energy is at some pressure and temperature. But what we know to start with is that we have the Gibbs free energy of some pure substance at a temperature of interest, but not at the pressure that we want. So we let's say this fellow here pertains to room temperature and also 1 atmosphere. But over here, we want the same temperature, room temperature, but let's say a pressure greater or less than 1 atmosphere. It really doesn't matter whether it's greater or less. Just for the sake of argument for discussion, we'll call it greater. So now we need some kind of correction that we need to add to get us from the standard state here at 1 atmosphere and room temperature up to room temperature and some higher pressure. So what's that going to look like? Well, if you remember that dg is equal to VdP minus SdT. Then if we hold temperature constant, as we are here, because we're going to look at everything at room temperature, then dg is equal to, or rather dg dP is equal to V. So what we can do, let's erase the chalkboard, is the Gibbs free energy at pressure and temperature is going to be equal to the Gibbs free energy of the standard state at room temperature plus an integral where we integrate from 1 atmosphere pressure to the pressure of interest, putting over here dg dP, which is equal to V, and then dP. So we're going to integrate over this. This thing here is our dg dP. So that's equal to V. All right, so here also let's identify this. P naught is equal to 1 atmosphere. It doesn't really have to be our standard state. It could be any pressure or any temperature we like, but it'll just make this a little more convenient. So if we have this fellow here, if we're compressing a liquid or a solid, the change in volume is very small. We could maybe consider it constant and pull the volume out here. But if we have a gas, then the volume is going to change considerably. So what are we going to put in terms of volume? If volume is a function of pressure, we need something called an equation of state that will relate those two. Well, we will use the simplest of all equations of state and use the ideal gas law, where N is the number of moles, R is the ideal gas constant, T is temperature, and that is divided by P. So that is the ideal gas law. So we'll put that into this integral here, and that will give us the Gibbs free energy. This is what we're after at some pressure and temperature, is the Gibbs free energy of the pure substance at the standard state and temperature plus this correction where we have nRT over P and then dP. And then we have P naught. Let's just put that as 1 atmosphere over here. And then the pressure of interest. Now these are constant, N, R, and T, so we could pull those out of the integral. And then if we do the integration, we get this is equal to G naught and T plus nRT multiplied by the natural log of P plus nRT multiplied by the natural log of 1 atmosphere. But the natural log of anything that is equal to 1 is going to be 0, so this whole term gets knocked out, and we have this. G as a function of pressure and temperature is G as a function of temperature plus this pressure correction, nRT times the natural log of P. Now, N is the number of moles. In another video, we explain how G divided by N is equal to this thing called the chemical potential. And so we can rewrite all of this, divide out everything by N, this by N, that by N, and then this by N. So if we divide everything by N, this becomes a chemical potential. So does this, and then that N just drops out. So we have chemical potential at pressure and temperature is the chemical potential of the standard state, the temperature that is given, plus RT, remember the N over here disappears, multiplied by the natural log of P. So now that we've got this equation here, how does fugacity come in? Well, it comes from the fact that we assumed that our system was going to act like an ideal gas. But let's say it's not an ideal gas. What we'll do is we'll make up a whole new function. This is what Gilbert Lewis did. He wasn't using chemical potential terminology. This didn't exist yet. But it's essentially the same idea conceptually, where we're just going to make up a new function. We'll call it f for the fugacity. And that fugacity term will make up for all of the defects of the fact that our substance, whatever it is not an ideal gas. And so if you've ever wondered where this RT natural log something comes from, and we have some kind of compositional variable, it comes from this. So we have F that stands for fugacity, which makes up for all the defects in the ideal gas. Now you could play other games, you could put in other equations of state. It's kind of fun to do that. You could stick in, let's say, the van der Waals equation of state and get a different kind of integral. But in the end, it's just easier to just shove all the mistakes, all the errors related to this assumption by making this thing F, where F will approach P as the ideal gas, as the gas in question, or any substance in question, approaches ideal gas behavior. So F becomes like pressure as the system approaches an ideal gas. So that's the fugacity. What about the activity? Well, let's come back and look at the integral. For the integral, we knocked out the P over P naught term. I don't want to write it there because that'll make the equation incorrect. So let's say we didn't have one atmosphere case. So we have this plus RT ln P minus RT ln P naught. For both of these, we could substitute fugacity. So at 1 atmosphere, our system might not really be an ideal gas. So if it's not, then we can write this as RT ln F minus RT ln F naught. So F represents the 1 atmosphere case where we have deviances from an ideal gas, and then F is the case for the pressure of interest, where the system is still not acting like an ideal gas. Let's go back and combine those terms. So we can have mu over mu at PT, and then that's equal to mu naught at temperature plus RT ln F over F naught, where F naught is referring to the fugacity at some standard state. Let's just call all of this equal to A. So the chemical potential at pressure and temperature is the chemical potential at temperature plus RT ln, oh, we forgot the T, RT ln A, where A is the activity. Now we're talking about mixtures, so we usually put a subscript I. So the activity of I is equal to the fugacity of I divided by the fugacity of I at some standard state. We'll just call it F naught. Well, I guess we could put a comma I there. This can be anything we want. It can literally be quite anything. And so what that means is there's no fixed value for the activity. If we have a system where pressure is fixed, so that's a constant, and let's say temperature is also a constant, and let's say the composition is also a constant. All these things can be constant, but that does not mean that this would be a constant. There is not one value for the activity if we have a mixture. If we have a pure substance, then the activity goes to 1. That's for a different video. But the bottom line is the activity will depend on what we choose as the standard state. So strictly when we talk about activities and fugacities also, these are describing components in particular phases. Let's write this a little bit neater. These are components in particular phases. It doesn't have any meaning in pure substances. So the activity of a pure substance, let's say the activity of SiO2 in quartz, that's a boring case. That just equals 1. So if you have the natural log of 1, again, the whole thing drops out. So if you Go back to the earlier part of the video, you can see that the chemical potential is then equal to the standard state. Remember, the standard state is for pure substances. So by definition, when we talk about activities or also fugacities, we are not talking about pure substances. These only have any kind of meaning when we are dealing with impure mixtures. And we can relate the two. The activity of I is equal to the fugacity of I divided by some fugacity at standard state. But since we have any choice we like for the standard state, then this value is not necessarily fixed. So these things can be variable, and it does make the whole concept of activities a little bit, well, let's say interesting when you start reading different kinds of papers and they are using different choices of standard state and they come up with different activities for describing the same kind of thing under the same kinds of conditions. But anyway, that's the general theoretical basis for ideas of fugacity and activity.